want to show some solution for the Y problem. So in this talk, I will firstly introduce some background for the Y problems, and then I will introduce the father-like interference. So by introducing this interference, so I will show some results for the Y4230 and other Y state. So in the following, I will also introduce the Nat'l structure along the 2.2 GeV, 4.2 GeV. So this state is very important to construct the Jeff-Psi family with. So I will introduce our progress in this for this study. So firstly, I will focus on the Y problems. So we know that in the 1915, so many light hadrons were absorbed by the experiment. So Gilman and Tsing proposed the Park model and found the SU3. So and to categorize these light hadrons into different representation. So they also predict the omega state, and then the experiment found this omega state. I think this is very important to construct the Park model. So we also face the Tsing situation. So in this slide, I will introduce the status of charmonic family. So we know that in 1974, many charmonic states listed in the particle data group were absorbed by the experiment. So in this slide, I list this charmonic-like state. So for describing the mass spectrum of this charmonic-like state, the Cornell group introduced the Cornell model. In this model, they proposed the potential, like the Cornell potential, to describe the charmonic family. This potential is composed by two terms. One is the linear potential. Another one is the Coulomb potential. So we know that according to this potential, so there are many theoretical studies for the metal for studying the metal family and the baron family. So different quark model were developed by the different groups. So since 2003, we also faced a new situation for the charmonic-like state. So in this slide, I also show some observations for the XYZ state. So according to the production mechanism, so we can find that there exist 5 groups. The first one is from the B decays, the weak decay. So there are many states. The famous one is X3872. The second group is come from E plus E minus ignition into the charmonic-like state. So in this talk, I will focus on this charmonic-like state. So we also have other groups like the E plus E minus ignition. So you can notice that the final state there exists a Jeff-Psi particle and plus a charmonic-like state. So the charmonic-like state can also be produced by the gamma-gamma fusion process. So in here, I list the 3 states here. So we also, I also want to emphasize another group. So like the charged charmonic state. So these states come from the hadronic decays from the Y4216. So so we can so if you have an interest, so you can find some review for this field. So I want to emphasize that so this situation is useful for us to identify the exotic state. So I think it's a very important issue in the hadron physics. So we know that the hadron include the conventional the state like the meson and baryon. So there also exists the exotic state like the molecule state, hybrid meson, global tetraquark state, and pentaquark state. So I think it's very important to identify the exotic state by combining with these observations. I also want to emphasize another point. The observed XYZ state can provide us good platform to identify the exotic state, and also can provide a chance to construct the GSI family. So in this talk, I will focus on these issues. So here I also show the experimental status from the E plus E minus accumulation. So you can notice that there are many Y states. So the first one is the Y4260. This state was observed in 2005 from the Baba experiment. They analyzed the E plus E minus to G psi pi plus pi minus and found a peak. So later, many experiments announced the observation for the other Y states. So in this slide, I list the observations for this Y state. I also want to indicate that the Y problem was proposed by the BEST3 corporation. In this corporation, so they wrote a white paper on the future physics program. So they indicate that there exists the Y problem. The Y problem is that how to understand this Y state, how to understand this lower phenomena. So in this talk, I will introduce our progress on these issues. So firstly, I will introduce the Faro-like interference. So I will introduce this interference effect to interpret the Y state. So firstly, I will briefly introduce the experimental status for the Y4260. So the Baba analysis the G psi pi plus pi minus environment mass spectrum and find a enhancement peak here. So you can notice that there exists a puzzle. The puzzle is that no evidence of the Y4260 in the R-scan value state and the open channel decay channels. So we also notice that there exists many theoretical explanation to the Y4260. So we can categorize these explanations into two groups. The first one is the exotic state explanation. So like the theorist introduced the charmonic hybrid and the diquark and anti-diquark state and the molecule state to explain the Y4260. So there also exists the conventional charmonic assignment to the Y4260. So, but I want to emphasize that if you want to introduce the resonance explanation to the Y4260, you have to face the difficulty. The difficulty is that you, according to the calculation from the exotic state model and the conventional charmonic assignment, so they predict that this state should exist in the open channel decay channel. So you can see that there does not exist any signal for the Y state. It's a problem for the resonance explanation to the Y4260. So for solving such difficult, so we once introduced a non-resonance picture for the Y4260. So we can notice the better experimental data. So you can notice that this enhancement is not symmetry. It means that you cannot simplify use a Brits-Wigner to describe this light shape. So we also noticed that in the E plus E minus to pi plus pi minus J psi closed section, so you cannot find the singular find the enhancement for the psi 41 60 and psi 44 50. So we know that these two charmonium-like states is well established in the PDG. So when we faced this situation, so we proposed that maybe this Y4260 can be reproduced by the interference between the psi 41 60 and psi 44 50. So we did a calculation in 3 papers. So we found that we can reproduce the experimental data well. It means that we can explain why two charmonium-like states like psi 41 60 and psi 44 15 singular are missing in the data. So we can also naturally understand why no evidence of the Y4260 in the R-value scan and the open channel decay channels. So I think the difficult can be solved by introducing the non-resonance picture of the Y4260. It means that the Y4260 is not a resonance in our models. So in the following, I also want to introduce the experimental data for the Y4360. The situation is similar to the Y4260. It means that so you can find that this enhancement exists in the psi 2s pi plus pi minus from the E plus E minus inclination. So the experimentalist also did not find the enhancement structure in the R-value scan and in the overtran decay channels. So it's the same problem as the Y4260. So following the same idea, so we also introduced the follow-like interference effect to introduce to explain Y4360. So in this paper, I show the result for our from our model. So you can find that finally we can reproduce the experimental data for the Y4360. So it means that we can use the same mechanism to explain Y4260 and Y4360. So in 2017, the best 3 give a more precise date of the E plus E minus to J psi pi plus pi minus. In these papers, they found that the singular of Y4260 contains 2 substructures. The first one is the Y4220, and the second one is the 4330. So this is the new data. So for explaining this new data, so we restarted this process by introducing a nanostructure Y4220 and considering the fiber-like interference picture. So you can notice that. So if we did not introduce the nanostructure like the Y4220, so you can see that we cannot describe the experiment data around 4.2 GeV. It means that we have to introduce a nanostructure Y4220 to describe the details data around the 4.2 GeV. So you can see that when we introduce the new structure here, so we found that we can describe the data, and we can also find that the Y43 13 can be killed. It means that the follow-like interference picture plays a resonant killer to the Y43 13. So in this slide, I also want to emphasize a point. The resonance parameter from our study is that it's a nano structure. So you can find the resonance parameters. The width is nano. So you must be asked a question: what is the Y42 20? So in the following, I will give an answer for this question. So in the another papers from the batch 3 experiment, so they studied the E plus C minus to H sub C pi plus pi minus. They also found the two resonance structure. The first one is Y42 20, and another one is Y43 19. So it means that more structure are reported were reported in the experiment. So we face the same situation, how to expand this Y state. So in this in our EPGS papers, so we also introduced the interference effect. I want to emphasize that the interference effect is very important to play the resonant killer for the newly observed charmonium-like state Y43 13 and Y43 19. It means that when we faced the new data from the batch 3, so we only need the Y42 20. So it means that we only need this. We only need to introduce another Y state here. So in this slide, I want to emphasize, give a summary for the situation of the Y state. So so we know that in the experiment, so there are many Y states reported by the batch 3 and the better experiment. So if we introduce the interference effect, so we found that the Y43 60 and Y43 90 can be killed in our model. It means that so we only have 3 states here. In this slide, I marked the Y42 20 as with the red color. It means that I will focus on this state and introduce our progress for explaining this Y state. So I want to emphasize that this Y state around the 4.2 GeV is a nanostructure. It's very important. So firstly, I also want to introduce some old work from the Cornell group. So in the 1918, so the Cornell group did a calculation for the charmonium mass spectra. So you can notice that they predict that predict that the 4s state is with the mass 4.4 GeV, which is consistent with the Psi 4415. It means that in this older paper, they propose that Psi 4415 is a good candidate for the 4s states in the charmonium family. So if you check the other theoretic calculation from after this work, so I think many theoretical groups adopt this conclusion. So in my talk, I want to emphasize maybe this conclusion is not correct. So later I will introduce our progress for this point. So I also want to introduce another paper from Quanta Zhao group. So in 1995, they did a calculation by considering the screen potential and found that the 4S state is about 4.2 GeV. This conclusion is different from that of a Cornell model. So this is I want to emphasize this point. So in the 2014, so we also studied this problem. So if you check the charmonium family and the Wu-Zheong family, so we can find the similarity between the GFPSI and the Wu-Zheong family. So you can notice that the mass gap is similar. So it means that the PSI 4S, the gap between PSI 2S and the GSI is similar to the Wu-Zheong 2S and the Wu-Zheong 1S. So you can use the you can find the similar way for the higher state. So if you notice that there also exists a mass gap along the 200 MeV corresponding to the mass gap between the Wu-Zheong 4S and the Wu-Zheong 3S. So we can use this mass gap to make a prediction for the PSI 4S. We found that the PSI 4S mass should be located at 4.2 MeV. This result is consistent with the screen potential prediction of the PSI 4S. So I want to emphasize that this one is very important. So maybe this one can provide a solution to explain the Y4220. So I also want to indicate another point is that this PSI 4S is a nanostate. According to our calculation, we found that due to the node effect, the width of the the width of the PSI 4S is a nano. So it means that we can conjugate that the PSI 4S is just correspond to Y4220. So I think this assumption should be tested in the experiment. So in the following, I also want to introduce some experimental evidence for the nanostructure exists in the 4.2 GeV from the batch 3. So you can notice that in the 2014, the batch 3 began to focus on this issue. So they measured the E plus E minus to GFPSI pi plus pi minus process and the E plus E minus to the H sub C pi plus pi minus process, and found that there exists the evidence for the nanostructure along the 4.2 GeV. So this is the experimental evidence. So later, the batch 3 also measured the E plus E minus to Chi0 omega process and found that there exists a peak exists in the 4.2 GeV with a nano width. So they also claim that the E plus E minus to Chi1 omega and the E plus E minus to Chi2 omega, the analysis that these two processes, they cannot find the peak. So if you take the mass of PSI 2S to be 4213 MeV, so you can find that this process, like the PSI 4S to Chi0 omega, is allowed. Another process, like the PSI 4S to Chi1 omega and the PSI 4S to Chi2 omega, are forbidden kinematically. So this one is can explain why only e plus e minus to chi 0 omega was reported by the batch 3. So focusing on this batch 3 data, so we also did a calculation to his hidden charm decay channels. So we introduced the charmonium assignment to the Y4220. So you can notice that if we introduce the psi 4s corresponding to this Nat'l structure around the 4.2 GeV, so we can reproduce the branch ratio for this process. It means that I want to emphasize that the cup channel effect plays a very important role to reproduce the branch ratio for this process. So you can notice that here we introduced the hadronic loop composed by composed of D-meson loop. It's D-mesons. So we can use this hadronic loop effect to describe the data. I think this conclusion is that this Nat'l structure exists in the 4.2 GeV, can be expanded as the psi 4s. This is our conclusion. So in another paper from our group, we also studied the E plus E minus to psi 2s pi plus pi minus process. So in this paper, we want to emphasize that missing psi 4s around 4.2 GeV exists in the psi 2s pi plus pi minus environment mass spectrum. So you can notice that there exists a small peak in the cross section data for the E plus E minus to the pi plus pi minus psi 2s. So we also give the resonance parameters by fitting the data. So you can find that this one is a Nat'l structure here. So we also propose that the experimentalist should be pay more attention to this structure. So we also studied the hidden trend, hidden trend decay channel for the psi 4s. So we studied the psi 4s to psi 2s pi plus pi minus and make a comparison with the experiment data. So you can notice that we can also reproduce the branch ratio from the experimental measurement. So it means that this one, this state introduced by our group, located in the at the 4.2 GeV, this state can correspond to the psi 4s state. So I want to emphasize this point here. So we also give a combined fit to 3 process, like the E plus E minus to psi 2s pi plus pi minus, and H sub c pi plus pi minus, and the chi 0 omega mentioned above. So we can find that we can get another fitting data for the resonance parameters for this Nat'l structure. So here I show these parameters here. Yeah. So in 2017, so the batch 3 measured the E plus E minus to pi plus pi minus psi 2s process. So you can notice that their conclusion. So they confirm of our prediction for this Nat'l structure exists in the psi 2s pi plus pi minus environment mass spectrum. So you can notice the data around the 4.2 GeV. There exists a small peak here. Okay, so if we want to explain the Y4220 as a psi 4s state, is a charmonium-like charmonic state. So we have to face the problem. So we know that for the higher charmonic, the dominant decay is the open channel decay channel. It means that this state should be found in the open channel decay channel process. So fortunately, we found an interesting paper from the batch 3 in 2019. So in this paper, they analyze the E plus C minus to pi plus D0 and D star minus process. So you can notice that there exists a peak around 4.2 GeV. It means that if this one can be confirmed by experiment, so it means that it provides a good evidence for supporting the charmonic assignment to the Y4220. So I think it's a very important progress for studying this nanostructure around 4.2 GeV. So I also want to talk about some lessons from the Pentapox studies. So we know that in 2005, the Pentapox CT plus were reported by the experiment list. So later, according to the high precision data, the JLab experiment says that they did not find this peak in the NK environment mass spectrum. So we know that the Pentapox event shows that we are still far from understanding the nature of QCD. So fortunately, after 10 years, so the LHCb experiment found the two Pentapox candidates, two PC states. I think there are many theoretical studies for this issue. So I also want to indicate that the status of charmonic family shows our poor understanding of the QCD non-perturbative behavior. So I want to indicate another point is that the Y4220 is a key point to construct the gypside family. So we know that there exist many charmonic states. So in this slide, I show some many charmonic states reported by the experiment. But till now, we still cannot, we still did not establish the gypside family. It's established for the charmonic above the 4.44 GeV. It means that, so you can notice that there exists a threshold, DD bar threshold. So we can find that if you face the charmonic state above the DD bar threshold, you can find many novel phenomena. So like the precise 4S state. So we still did not establish this state. So we have other problems for the high state. So I want to say that the Y state around 4.2 GeV with the nano structure is a key point to construct the gypside family, especially for the charmonic state above the 4.2 GeV. So in the following, I will introduce our progress for constructing the gypside family with update data of the charmonic-like Y state. So in last year, so we published a long paper. This paper, so we want to establish the gypside family with the Y state. So So I think it's important for our understanding for the Jeppesen family. So so in this slide, I want to show the situation, present situation of the charmonic family. So so you can find that there exists the state below the DD bar threshold. There also exist the many states above the DD bar threshold. So I want to in the following, I want to talk about our opinion for the description for the mass spectrum. So we found that the unquenched potential model is should be introduced in for constructing the Jeppesen family. So we can introduce the Hamiltonian like this way. So I emphasize that the linear confining potential, including in the potential, should be modified as these things. So it means that we should be including we should include the screen potential to describe the Jeppesen family. So we did this calculation. So we found that we can reproduce the mass of this observed charmonic state in the Jeppesen family, like this state. So I also want to emphasize that Y4.2 Y state around 4.2 GeV is an important scaling point to constructing the Jeppesen family, especially for the charmonic about 4 GeV. So you can notice that in our calculation, so we can get the mass for the precise 4s like this one. So the mass is about 4.2 GeV. So you can find that this theoretical mass is consistent with the experimental data. So we can also use this way. We can describe the other observed charmonic. So we can also use this way to predict some missing charmonic. So we predict many missing charmonic in this table. So in our work, we also introduced the mixing scheme from the 4S and the 3D. Why we need to introduce this mixing scheme? So you can notice that if we introduce the unquenched quark model, so we can give the predicted mass. So if you notice that if we take the mixing angle to be 0, it means that there are no mixing. So the 4S is above the mass of the Y4220. So if we introduce the mixing to 30 degree, so you can find that we can get the same mass as the Y4220. So it means that we need to introduce the mixing scheme to further study the Y4220. I also want to emphasize that. So this one, we also get the total width for the Y4220. So you can notice that this state is also a narrow state. The dominant decay is the DD star. It means that the vector D-meson pair is a dominant decay channel for the Y4220. So we can also find that there also exists the DD bar channel to pseudo-scalar state. So I think this open channel decay channel is very important for identify the Y4220 state. So I also want to
3 minutes.
Okay, 好. So I also want to predict the precise 4319, which is the pattern of Y4220. So I show some the decay width for this state. It means that the total width of precise 4319 has a significant enhancement. So I also noticed that in the DD2 decay channels, there also exists some hint for the precise 4390. So I think the future experiments should test this prediction. So in this slide, I also want to emphasize that the experimental evidence for the prediction of the precise 4390. So you can notice that if we introduce the precise 4390, so we can reproduce the data where this data is come from the e plus e minus to pi plus pi minus precise 2s. So I also introduced the 5s to 4D mixing scheme to explain the precise 4415. And we also can get the consistent results with the experimental data. So we can also predict another pattern for the precise 4415. It means another precise state along the 4.5 GeV. So in this slide, I also want to indicate that we still need more precise data of the resonance parameter of the precise 4415. So we know that if you collected the data from the experiment, so you can find that the resonance parameter for the precise 4415 is not good. So it means that we need more data. So if we have more data, so we can test this mixing scheme for the precise 4415. So I think I can finish my talk. So I will give a summary for my talk. So the white state from the E plus E minus inclination, I think is very important to construct the high charmonic family. So I think it's a research field for of the opportunity and challenge. So we also need more theoretical and experimental effort to this this issue. Okay, thank you very much.
Thank you. Question from the audience?
So Xiang, I stop. I have one feeling when you guys doing all this exotic states. Okay, whenever you find some states, you always find some two particles, the mass is close, and then in doing fitting, and then you always find a way to say, okay, I can produce this. So is there a more systematic way of doing such analysis?
Yeah. So when we face many white states, so for theorists, so we have a puzzle for this situation. It means that if we have a more white state here from the experiment, so we have to introduce the you can introduce the exotic state explanation to this white state, but unfortunately, so we cannot understand such more state. It means that we have to face the difficult to explain the white state only by introducing the exotic state here. So in our studies, I want to emphasize that maybe this white state can be if we introduce the interference effect. So we cannot. We only need to 3 states here. So it's I think in this one it's important. It's simple for us. So it means that we can find that the Y4220 this state can be assigned to the GFI family. It means that we cannot we did not introduce the exotic here. Yeah.
Further comments?
No, I'm fine.
Any other question from audience? If not, let's thank Professor Liu again. Our second talk will be from on-site speaker.